Hello everyone, we will start chapter 8 today. It's called linear differential equations of order n. So the goal for this chapter is this. We want to solve linear differential equation with order n. So we want to solve differential equation with order n. So in chapter 1, we only solve the first order differential equation, right? Linear differential equation. So I'm going to give you some examples here. Like this kind of differential equation, we have second order. And this is homogeneous, right side equals 0. And we are also going to solve maybe this kind of differential equation. The right side may be 4x squared, o times sine x, whatever, o plus e to the x. So maybe complicated, but it's higher order differential equation. Okay. And firstly, let's do 8.1, which is general theorem. So we are going to learn some definitions. Firstly, I'm going to introduce a very important definition. It's called derivative operator. So let's see. Definition 1 is called derivative operator. So what's the meaning of this one? I'm going to give you, let's do this from the example. It's a little easier, okay? Let's see. Right now we have a variable, the variable is a function, okay? And d is the operator. So if d means take the derivative of the function, means the first derivative, okay? And if we have like a d squared f, that means second derivative of the function. And in general, if we do d to the kth power f, that means the kth order derivative. So that's why it's called the derivative operator. So it just means what's the order of the derivative. Okay. So this is the definition. For example, what is d3f? That means the third derivative of the function, right? And next we have a general differential operator of order n. Operator of order n. So let's take a look at this one. General. So we write down general as this case, dn plus a1d to the n minus 1. So it's kind of like a polynomial, an minus 1d plus an. Okay, so what's the meaning of that one? So this is whole operator. That means ly. Okay, ly. And the y is the function. That means, so let's see, corresponding to dn, that means nth order derivative of the function. And a1 y to the n minus 1 derivative, and plus what here? So a minus 1 y prime. And be careful here. An means no derivative. Okay, no derivative, but it just means original function here. Just be careful the last term. Okay, even is constant. So constant is like a 1 to the function, so still keep the function there. Just be a little bit careful. Okay, I'm going to give you several examples here. And let's see. And the property are like, okay, we can do the property firstly. So which is ly1 plus ly2, lky equals kly. It's just like a satisfy the sum rule and constant of multiple rule. Okay, so let's take a look at example 1. If l equals d squared plus 4xd minus 3x, then find ly. Let's see, what is ly? Ly means firstly, d squared means second derivative, right? And plus 4x times the first derivative minus 3x is like a constant compared to the function, whatever. So 3x times y, like this. 3x means doesn't do any derivative to y, just keep the y there. Let's see. What is L sine y? L sine y should equals to like a sine second derivative. So plug in sine y second derivative and plus 4x sine x derivative and minus 3x sine x. Simplify. Sine, first derivative is cosine, and do another derivative to mean negative sine. And the second derivative of cosine. So this is the solution. Let's see how to find x, Lx squared. Lx squared should be x squared second derivative plus 4x x squared first derivative, right? Minus 3x times just x squared. And first derivative 2x, second derivative should be 2, and plus 4x times 2x minus 3x cubed. Simplify, should be 2 plus 8x squared minus 3x cubed. Let's see, I'm going to give you one exercise problem. D equals this one, d squared minus x squared d plus x. Let's find what is L e to the 2x. Okay, please try this by yourself. I'm going to give you the solution. L d squared means second derivative of this function. D means the first order of this derivative, and plus x times e to the 2x. No derivative to this function, just copy the function. And e to the 2x derivative is 2 e to the 2x because of chain rule, right? So take another derivative 2 e to the 2x derivative, which would be 4 e to the 2x, and this is the second derivative of the e to the 2x. So second derivative of that one should be 4 e to the 2x. And the first derivative is just e to the 2x. And if we take the e to the 2x out, factor this out, so going to be 4 minus 2x squared plus x. Okay, so this is the definition for the operator. Let's see. Next definition 2. For the general nth order linear differential equation, general nth order differential equation, so we write down a n like a y to the nth like a derivative plus a1 y prime plus a naught equals fx. Okay, so this is the differential equation, general form. And here, if the right side fx equals 0, then we say this differential equation is homogeneous. Otherwise, it's called non-homogeneous. Okay, so let's see. In the future, we want to rewrite this linear system as what? As this form, operator way, Ly equals f. Let's take a look at this example. Y to the third derivative, x squared second derivative, e to the x times y, which is x cubed. Okay, for this one, we can write down this as what? In operator way, it's going to be d cubed plus s squared d squared minus sorry here, y prime. So it should be sin x d and e to the x y equals x cubed. So you can see this is ly equals f form. Okay, operator way. Next, we have theorem 1. Theorem 1 says the set of all solutions to the nth order differential equation, okay, has like a, the solution set is going to be dimension n vector space. Okay, so that means what? You can take a look at this one. L equals d squared plus a1x d plus a naught x. So for this homogeneous differential equation, we noticed that this is the second order differential equation. So for the second order differential equation, we should have two solutions. So two solutions are like y1, y2, and then general solution is just a linear combination of those two solutions. Actually, we can also say y1x and y2x is a basis for the general solution. You can also say this one. y1x, y2x is a basis for the general solution. Okay, for the general solution. So definitely we know the basis, the number of the basis is dimension, so dimension is 2. For second order, dimension is 2. Third order, dimension is 3. Means we have 3 solutions. In general, you can see if for the nth order differential equation, we should have n solutions. And what's the general solution? Linear combination of those n solutions. Okay, that's the theorem 1. Now let's take a look at the example. So for the example, we are going to solve a second order differential equation. Let's take a look at example 1. Determine all solution to this differential equation. And the solution to this differential equation has this kind of form. Y x equals e to the rx form. R is a constant. And then use the solutions to find the general solution. So let's see. Because all the solution has this form, so we plug e to the rx into the solution. This should plug into the differential equation. This solution should satisfy the differential equation. Now let's see. We plug this e to the rx into the differential equation, and let's see. The second derivative of the y should be r squared e to the rx, right? And plus r e to the rx minus 6 e to the rx, and we factor e to the rx out, and we get this thing. We get e to x times this quadratic function equals 0. And we noticed e to the rx is exponential function. If we look at the graph, e to the rx never equal to 0, right? The range is always greater than 0, so it's never equal to 0. So in order to have this equation, we just have this equals 0. That means r equals -3, r equals to 2. Then we get two solutions, e to the -3x, e to the 2x, right? So the same as the theorem, you can see second order differential equation, we get two solutions. But what's the general solution? Linear combination of those two. So what's the general solution? c1 e to the -3x plus c2 e to the 2x. Actually, they are also independent. You can use the Wronski to prove they are independent. So, but it's always true. We don't have to. So we say this is the general solution. Those two functions is a basis to the solution, general solution set. Now let's take a look at this exercise problem. Second order differential equation, same thing, has e to the rx. What we want to do? Just solve for e to the solve for R, right? And after we solve for R, we get 2R. So we get two functions, y1, y2, and linear combination. Here's the solution. So now we know how to solve homogeneous differential equation. Next, we are going to solve non-homogeneous differential equation. Let's take a look. Non-homogeneous solution means the right side, capital F, is not 0. This is called non-homogeneous. We have a theorem too. Let's see. If y1, y2, till yn be the linearly independent solution set to the homogeneous differential equation, homogeneous, and yp is a particular solution, then what's the general solution for this non-homogeneous solution? Is made by two forms, okay? Is addition, so you can see I'm going to circle like this way. This is the solution to the homogeneous differential equation, and this is the particular solution satisfy the non-homogeneous. So this is the general solution. General solution is made by non-homogeneous solution plus particular solution. Let's take a look at the proof. It's pretty easy. So if we plug this into the differential equation, Ly, we just write down like this way. Write down like this way, right? And then we separate, because L is the linear operator, so we can just separate them. After we separate them into homogeneous and particular solution, and we noticed homogeneous is Ly equals 0, so we get 0 here. And this is the particular solution, so that should be F. And 0 plus F is F. So you can see Y satisfy Ly equals F non-homogeneous. This is the proof. Now let's take a look at example 2. We want to verify 1/3 e to the 5x is a particular solution to this differential equation. So we just want to plug in this into the differential equation and see if this particular solution can make the equation true. So let's see, when we plug in to the left side, so second derivative of this one should be 1/3 25 e to the 5x minus 5 e to the 5x, that's the first derivative, minus 2 e to the 5x. Okay, and now simplify, we factor e to the 5x out and combine all the other numbers together. So you can see e to the 5x, and here is 25 minus 5, 20, 20 minus 2 should be 18. So this is 6 e to the 5x, exactly same as the right side. So yp is a particular solution. If we want to solve, so we can say this is the first question, verify is a particular solution. If we want to solve this differential equation, so let's see, y prime minus 2y equals 6 e to the 5x. So by using the theorem 2, what's the general solution? The general solution should be the homogeneous solution. So it's going to be c1y1 plus c2y2 and plus the particular solution, right? Because this is second order, we have y1, y2 for the homogeneous. So we can solve for the homogeneous. It's like y double prime minus y prime minus 2y equals 0. So this is same as example 1. When we plug in e to the rx, it's going to be something like this. And we say this never equals 0, so r minus 2, r plus 1 equals 0. So r equals 2, r equals -1. So what's the solutions? The solutions to the homogeneous should be 2x plus c2 e to the -x. So this is solution to Ly equals 0, right? And what is the general solution to the non-homogeneous? We add the solution to the homogeneous differential equation plus the particular solution. The particular solution is given here. Okay, so this is the general solution to the non-homogeneous solution. So we can just write down non-homogeneous solution here. So this is the solution by using the theorem. Now let's take a look at, we can try this exercise problem. So we want to determine a particular solution. And the particular solution has this form: yp equals a naught e to the 3x. Okay, and also find the general solution to this differential equation, third order differential equation. Like this one. Firstly, particular solution is not given exactly, but the form is given. So we need to decide what is a naught. Because this is particular solution, so it should satisfy this differential equation, right? Here's the solution. So we plug the yp into the differential equation, and we want to solve for a naught. So let's see. The third derivative of that one should be 3 to the third power, so should be 27 e to the 3x plus 2 a naught times 9 e to the second order derivative, and third order derivative minus 2 a naught e to the 3x equals 4 e to the 3x. So if we factor e to the 3x out, so 27 a naught plus 18 a naught minus 3 a naught minus 2 a naught, and equals 4 e to the 3x. So you can see if we cancel e to the 3x, that means this should equals to 4. Let's simplify. This will be 45 minus 5, right? So that means 40 a naught equals 4. That means this is 4 over 40, which is 1 over 10, which you can write down 0.1, either way. So what is our particular solution? Particular solution should be, this is the particular solution. Next, if we want to solve the general solution to the non-homogeneous differential equation, first step, we need to also need to find the homogeneous differential equation. So first order differential equation, that means we want to find e to the rx such that satisfy homogeneous equals 0. So when we plug in, same as before, we will get r cubed plus 2r squared minus r minus 2 equals 0. And this doesn't equal to 0, so that means this equals 0. And we want to factor this out, okay? And I'm going to combine those two terms together and factor r out. And combine those two terms together to r squared minus 1. So you can see they both has r squared minus 1 and r plus 2 equals 0. Further factor r squared minus 1, so it becomes r plus 1, r minus 1, r plus 2. So what's the solutions for r? 91, 1, negative 2. So what is the general solution to the homogeneous? Negative x e to the positive x e to the negative 2x. So this is solution to Ly equals 0, right? And the particular solution, we also get that in the last step. So this is step 1. Here is step 2. So what's the general solution? Y equals the sum of the general solution to the homogeneous and plus the particular solution. That is general solution to non-homogeneous differential equation. Okay, so that's all we need to know for this section. Let's take a look at the summary. Summary for this section. Firstly, we learned operator way, and we learned what's the meaning of homogeneous and non-homogeneous, right? And L is the operator, derivative operator. So that means d, for example, d squared plus d minus 2d minus 2 y means what? Second derivative plus the first derivative minus 2y means this one. So sometimes we write down in the operator way. And number 2, solve general solution for homogeneous differential equation. So it's going to be c1 e to the like r1x, c2 e to the r2x. And if this differential equation is order 2, we have two solutions. If it's order 3, we have 3. If n order n, we will have n. And the general solution is just linear combination of all those. And thirdly, we solved the non-homogeneous differential equation. That means the solution equals what? C1 e to the, okay, so let me write down this way. C1 y1 plus general Cn yn plus yp. Solution to homogeneous particular solution to Ly equals f. Okay, so in the next 2 sections, we will continue to solve more complicated differential equations like order n.